Hello, in this video we're going to look at the probability of being in the first quadrant when we're dealing with a scaled bivariate normal random variable. And scaled here means that the variances are 1, the means can be anything, and the correlation can be anything. I have some background videos integrating a bivariate normal distribution. There we show that it integrates to 1. Here we calculate some probabilities where we're in a standard bivariate normal case, and we're going to make use of BV4, which is integrated in a rectangle and polar coordinates. Now, something that I don't put in the background videos, but sort of the purpose of this is that we're ultimately going to calculate power and sample size for the multivariate sign test, but I need to build up to it so I can reference these videos when I get to that point. So the problem is that we have a multivariate bivariate normal random variable, mean mu, and so that really should say mu1 and mu2. We're standardizing the variances at 1. That's the scaled part. The correlation row can be anything. We want to find the probability that x is positive and y is positive, and that's the first quadrant. So now the solution is, from BV1 I show that we can kind of partition or separate this bivariate normal into 2 pieces, this and then this, and that's going to ultimately help us integrate this, because if we integrate y first, this is a constant, can come out and we can just focus on this. And that's what we do. So the integration, or the probability of being in the first quadrant, is this. So we integrate over the first quadrant of our bivariate density. And we're going to make a change of variable technique. So here is our region. So this is x is positive and y is positive. And we're going to transform it to this, where we let z be this piece, which is essentially this piece, but we bring in the 1 minus rho squared. And if we bring it in into a squared, we take the square root, so when we square it we get that back. So this is it. And then we when you're mapping this, I like to map edges to edges in this mapping, and then it helps me focus on where the region is. So this is side number 1. This is where x is 0. So you come over here, x is 0, and then so we know that in this case we're on this boundary, and y goes from 0 to infinity, and when it's 0 it's this point, and when it goes to infinity it goes up. And so then we can solve for y, dy dz is this, and then we'll put this back into this region. But this is the region that we're integrating over. And this is the line in this region, right here. So now we put in z for that piece up here, and then when we plug in our region, we're integrating from that line that we saw to infinity, 0 to infinity. And I don't like this piece right here. So what I'm going to do is transform that. Let w be this piece in the middle, and then dw dx is the same, and we get we just get this, and then so we get this, the e to the w squared. So that's this piece here. But then when we integrate from 0 to infinity, we actually go from minus mu1 to infinity. And then here, what we can do is we can use, this is kind of an ugly thing to integrate, and we're going to attempt to simplify it, but you could just put this in Wolfram Alpha and it pops out a value. It's very easy. But I want to be able to do this in base R. Now I say base R because you can download a package and do a double integral in R, and you'd come up with the same thing as Wolfram Alpha. But for just I guess ultimately fun, I try to simplify it and just use base R. So that's what the next few steps are going to be. So remember, we're in this region initially, and then we transformed it. So this is basically a shift to the left. So then so this line is now over here, which is what this is. And but then we want to like this is you know, this we're going to because we're in the w squared z squared. That's kind of a tough thing to do. So what we do is convert it to polar coordinates. So we're going to convert this to polar coordinates, and then we get this. So x is r cosine theta, y is r sine theta, the Jacobian is r. Then then it reduces to this. Now I put a question mark here because integrating this over in polar coordinates is not that straightforward. So now let's examine this region in a little more detail. So, you know, think about it as a ray. You know, that's the r, and then theta is the angle. So this can go to 0 to infinity all the way, but then once it gets past this, it may touch that. So integrating this region is, I think, going to be pretty easy. But then integrating the second region, so we'll do this in 3 pieces. Here, the angle, of course, is easy. It goes from here to here. But then the r, the radius, is kind of stuck on that line there. And this is where BV4 comes into play, integrating a rectangle in polar coordinates. We show how to do that, to integrate over basically a line. And then the same way here. So if we're integrating, we're integrating this piece, but once we get to this angle, the radius doesn't follow that line, it follows this line. So then we have to think about it going again. And as the line goes like this, it gets longer and longer and longer and longer and longer, ultimately to infinity. But once we get here, then we'll stop. So we're going to integrate this in 3 pieces. So region 1 it's actually already solved, and we did that in BV2, and this is the answer. It's a nice clean answer. Now region 2 is this region, and we know the distance here is mu1 and the angle is theta, and so as we go from here to there, so that radius, you know, we're always in sort of a right triangle setting, and so we know that we can solve for this theta. This theta, which we're going to call theta star, is the arctangent of mu2 minus rho mu1 square root of 1 minus theta 2, and we get this angle is this, and it's because that we know where it intersects here from the first page in our transformation. So we know this side of the triangle and we know this side of the triangle. So the tangent of that is this over this, and then you take the arctangent to solve for this theta here. And the reason I do that, because theta has to go, you know, it goes from here to here. So it goes from pi over 2, you know, to pi plus this angle here. So our integral, and then to this distance r, if we look at the cosine of theta, which is mu1 over r, then we can solve for r, and r ends up being mu1 divided by cosine of theta. And so, and that's what r, so r kind of goes on this angle here. So anyway, so it boils down to the radius is we're going from 0 to this, you know, mu1 over cosine theta. And we're going from 2 pi to pi over, or pi plus theta star, which it is this, right? Pi plus this theta star. Well, let's let u be this piece here, minus 1/2 r squared. We can, du is minus dr, r minus r dr. Then this becomes this piece here, and then that's a constant come out front. The antiderivative e to the u is just e to the u, and then we plug in our constants, and we get this piece right here. Well, now this piece is integral in terms of one variable, which is very easily done in R, base R, with the integrate function. And I will put the function that I use to calculate this in the comments. So I'm a put an R program that calculates this overall probability, but you have to do it in pieces. So I'll put the R code to do this. And then the last region is this. So the distance between two parallel lines. So we know this line, and then this is this line without the y-intercept. And so then to find the distance between these two is a standard problem, you know, and it ends up being this distance is mu2. And I didn't go through the calculations because the video is already getting long. But then to find this angle, we found this angle in BV2, I think, and then this angle ends up being the same as this angle. You'd have to do that in your mind. So then we know that this is the arctangent of that thing, and this is the arcsine of rho. So then we can take pi over 2 minus those to get this angle. And so we know this angle here when we're integrating. It ends up being, you know, pi plus theta star, you know, go from here to here. And then we go to 2 pi minus this arcsine. Now the radius, or that goes along this line, if you look at the cosine of theta, it ends up being mu2 over that radius. Then you can back solve for the radius, and then we'll plug that in here. Oh, I already do. And then so I skip a few steps to get to this piece here. So this is that cosine that I was telling you about. But when we take the cosine, we only want this piece as it grows, not the whole angle. So we add some and then subtract this theta that goes here, so it becomes specifically the angle that we need to calculate this radius. And so this is it. Well, that's all I have for today. So in my comments, I'm going to put two things. One, I'm going to put a little R simulation that simulates this probability of being in the first quadrant in a scaled bivariate normal. I'll do 1,000,000 reps of it, and it goes very fast. It's just a few lines. And then we will put in the R code to calculate these probabilities. And this is ultimately going to help us find power and sample size in the multivariate sign test. Well, I hope you enjoyed that. I sure did. Please like the video and subscribe so you don't miss the next one. Thanks. Bye.